Welcome to The Explainer. Today, we are going to talk about a super powerful tool that helps you find the real signal. You know, the important stuff that's hiding in a world full of noise.
This is a question we face all the time, right? Whether it's in business, science, marketing, you name it. Is this ad really working better? Is this way of doing things actually more efficient? And when you've got real decisions to make, guessing, well, that's just not going to cut it.
So, to really get a handle on this, we're going to follow a company. We'll call them Chemetech, as they tackle a really common and super important business problem. And we'll see how they use a pretty neat statistical tool to solve it.
All right, so here's the deal with Chemetech. They've got this awesome new water filtration system. The thing is, they have 3 different ways they could assemble it: Method A, Method B, and Method C. And the big million-dollar question is, which one is actually the most productive? I mean, this is a huge decision, right? They absolutely cannot afford to just guess.
Okay, so let's dive right in. Before we even think about looking at any numbers, we've got to make sure the test is fair. I mean, the way you set up the experiment, it is everything. It's the only way you're going to get an answer you can actually trust. So to make sure there's no bias, like accidentally putting all your fastest workers on one method, Chemetech does something called a completely randomized design. It's pretty straightforward, really. They just take 15 workers, randomly split them into 3 groups of 5, and then, you guessed it, randomly assign one of the assembly methods to each group. Totally fair.
Okay, a little bit of terminology here, but it's easy, I promise. First up is the factor. That's just the fancy word for the main thing you're investigating. So for Chemetech, the factor is, of course, the assembly method.
And the different versions of that factor? Those are called treatments. So in our case, the treatments are pretty simple. Method A, Method B, and Method C. See? Easy. And last but not least, we have the response. This is just what we're measuring to see what happened. It's the outcome. For Chemetech, the response is the number of units produced by each worker. That's what they're counting.
All right, so after a week, the experiment is done. And here's the data they got back. You can see the numbers for every single one of the 15 workers. And look down there at the bottom. Those are the averages for each group. We've got 62 for Method A, 66 for B, and, only 52 for Method C.
So, looking at those numbers, you'd think, okay, Method B is the winner, hands down, and Method C looks like a total dud. But wait a second, is it really that simple? I mean, couldn't this just be random luck? Maybe the folks in Group C just had a bad week, How can we be absolutely sure that this difference is legit and not just, random noise? And that question, that's where the magic of a technique called analysis of variance, or ANOVA for short, comes in. Honestly, the core idea behind it is just brilliant. Think of it like this. ANOVA helps us separate the important signal from all the distracting background noise.
So here's how it works. ANOVA basically looks at 2 kinds of variation. On one hand, you have the signal. This is the difference between our groups. How different is the average for Method A versus B versus C? That's our potential effect. On the other hand, you've got the noise. This is the random variation inside each group. I mean, even when people are using the exact same method, some will be a little faster, some a little slower. That's just natural random static. So it all boils down to this one simple question. Is the signal strong enough to actually be heard over all that noise? We can only be confident that there's a real difference between the methods if that signal, the difference between the group averages, is way, way louder than the random noise happening within each group. Okay, so how do we actually measure this? Well, that brings us to something called the F-test, which is going to give us our statistical answer. So statisticians have this really cool way of boiling it all down to a single number. It's called the F-statistic. And the concept behind it is just beautifully simple. It's literally the signal divided by the noise. That's it. So a bigger F-statistic means you've got a much stronger signal. So when we run the numbers for Chemetech's experiment, what do we get? We get an F-statistic of 9.18. Think about that. That means the signal, the difference between the methods, is more than 9 times stronger than the random background noise. Wow. Yeah, that sounds pretty big, right? Okay, so what does that 9.18 actually mean? Well, it translates into something called a p-value. And in this case, the p-value is 0.004. Here's the deal with p-values. This number tells you the probability of seeing a result this strong just by random chance. So a p-value of 0.004 means there's only a 0.4% chance, less than 0.5%, that we'd get these numbers if all the methods were really the same. That is a tiny probability.
It's basically the data screaming at us that something real is happening here.
And that brings us to the final verdict. With a p-value that low, we can confidently say, nope, this wasn't just random luck. We have what's called statistically significant evidence that the assembly methods are not all created equal. The difference that Chemitech saw? It's real.
And you know, all of this number crunching gets summarized really nicely in a standard table like this one, an ANOVA table. It looks a little intimidating at first, but it's not. See that line for treatments? That's our signal. And error? That's our noise. And look, right there are the numbers we've been talking about. Our F statistic of 9.18 and that tiny p-value of 0.004. The whole story, all in one place.
Okay, so that's cool for Chemitech, but why should you care about all this? Well, because this amazing method for finding a real signal in all the noise, it's not just for factories or science labs. Not at all.
This tool, ANOVA, it's used everywhere to make smarter data-driven decisions. Think about it. Marketers comparing which ad campaign brings in more sales. Web designers testing which website layout gets more clicks. Farmers figuring out which fertilizer grows the best crops. Even banks use it to measure wait times at different branches. It is an absolutely fundamental tool for anyone who needs to compare more than two options.
So, the next time you're looking at 3 or 4 or maybe even 5 different options and you really need to know which one is best, don't just guess. Remember the simple logic of ANOVA. Remember to think about separating the signal from the noise, and then ask yourself this final question. Where could you be using this to find the real signal hiding in your noise?